Good afternoon.
Good afternoon.
Good afternoon. Good afternoon. I am Lawrence Bridgemohan, and I'll be presenting today on a conceptual framework for the analysis of shear damage in foam bitumen stabilized materials. Globally, with continuing infrastructural development, there's an increasing demand for quality pavement aggregates. Accompanying this demand, however, are concerns of diminishing supplies and environmental degradation with increased quarrying activities. As such, there's a renewed emphasis on more sustainable approaches to pavement engineering practices. The foam bitumen stabilization technology allows for the improvement of both reclaimed pavement materials as well as a wide range of locally available aggregate materials. Foam bitumen is described by the Virgin Co-Recycling Manual as a temporary state of reduced bitumen viscosity. It is produced when hot bitumen comes in contact with cold water in the presence of pressurized air. The result is this temporary expansion of foam bitumen. When mixed with the parent material aggregates, the increased surface area from temporary expansion allows for the coating of the finer particles within the aggregate skeleton. Upon compaction of this material, the bituminous mastic produced between the fine particles and the foam bitumen is described as conceptually spot welding the coarse, uncoated aggregate materials within the aggregate skeleton. Foam bitumen stabilized materials, referred to as BSMs, have been described by Fu to possess a microstructure consisting of an uncoated large aggregate phase, a foam bitumen fine filler bituminous mastic phase, and an uncoated mineral filler phase. Owing to this microstructure, researchers such as Jenkins and Collins have further described BSMs as a treated granular material or treated aggregate material with maintained granular characteristics, but with a notable improvement in cohesion. It is as a result of this maintained granular characteristics that BSMs are described as displaying stress-dependent behavior, with previous researchers identifying permanent deformation and shear strain accumulation as the dominant response of the material in its long-term life. Foam bitumen stabilization technology and BSMs continue to be used in the construction of pavement bases and sub-bases both locally in Trinidad and Tobago and more extensively in the global. Some of the more commonly referenced manuals and guidelines for the use and construction of bitumen stabilized materials are those that have been derived from South African research. These include the technical guidelines into the design and construction of bitumen stabilized materials by the Asphalt Academy of South Africa, as well as the Virgin Co-Recycling Technology Manual produced by stabilizing specialist equipment manufacturer, the Virgin Group. Notably, these both guidelines and manuals include materials classification criteria, which emphasizes on strength and stiffness properties. In addition, a recipe-based mix design process is adopted with a limitation towards an optimized foam bitumen binder content and a variable foam bitumen binder content and an active filler content limited to a maximum recommended range of 1%. Indeed, the characterization and classification processes within these guidelines allow for an optimized material performance as well as improved structural design process. Notwithstanding this, however, permanent strain development and mix design compositional factors have been identified as critical areas for research towards improved design. In fact, the significance of damage analysis studies towards improved pavement material characterization and design is established in previous studies on similar commonly utilized pavement aggregate materials. These include asphaltic concrete materials and its fatigue damage analysis, as well as unbound granular base aggregate and its rotting damage analysis studies. Additionally, having been included in some of these previously identified pavement material damage study applications, the dissipated energy concept has established itself as a valuable tool, serving as an indicator of energy release in response to repetitive loading and accompanying irrecoverable deformation. Particularly, damage analysis and dissipated energy have been utilized in asphaltic concrete studies, such as that by Majori et al. For investigating fatigue life, as well as asphaltic concrete studies by Guzman and Carpenter for classifying and comparing mixes based on its damage response. Similarly, its application in unbound granular aggregate studies include that by Tao et al., where damage analysis was used to characterize its rotting damage and identify the transition from stable to unstable behavior with increased repetitive loading. It is in this regard, and considering the significance of SHEAR behavior in the long-term response of BSMs, that a study into the use of dissipated energy in analyzing SHEAR damage of bitumen stabilized materials proposed. The goals of the study are to evaluate the relationship between rate of permanent SHEAR strain and dissipated energy for variable constituted BSM mixes, to characterize the SHEAR damage response of bitumen stabilized mixes using dissipated energy, and to allow for introduction of a more mechanistic approach to classifying these mixes. The study proposes to investigate the laboratory performance of 4 bitumen stabilized crustal mixes of varying combinations of 4 bitumen content, active filler type, 2 in fact of cement and hydrated lime, and variable active filler contents. Triaxial testing are to be carried out to provide stress strain data for determining shear strain accumulation of the material and dissipated energy data. In essence, the study proposes an examination into the dissipated energy response of variable BSM mixes. An evaluation of the dissipated energy versus number of cycles is proposed to identify stages in dissipated energy response, with indicators such as steady states of dissipated energy with increasing repetitions to serve as a representation of an adaptation to loading. Similarly, an examination of the relationship between permanent strain rate and dissipated energy is proposed to allow for characterizing the shear damage response of the material and identify the transition from stable to unstable behavior as loading progresses. It is projected that analysis of obtained data will be able to identify the incremental material changes of the mixes with increasing repetitions, the identification of the impact of variable binder content, active filler type, and content on its response and on its damage progression, and to allow a performance-based classification of the variable mixes. In summary, this presentation aims to highlight BSMs as an enhanced aggregate material with maintained granular characteristics and increased cohesion. Previous researchers and established material guidelines have identified shear strain, permanent deformation damage as a dominant distress response of the material. As such, a proposed study into the shear damage response of the material using dissipated energy is identified as a critical area for exploration. It is expected that this study can allow for characterization of bitumen stabilized materials, long-term deterioration, and examination of the impact of mixed variables on its behavior, all towards an improved classification process. Thank you for the time and welcome any questions that you may have.
Thank you, Mr. Bridgemohan. We have questions for you.
Thank you.
From a life cycle perspective, do you think unpaved roads especially agricultural roads, be replaced with a BSM pavement structure?
Yes, it has, in fact, the technology which has originated in South Africa involves applications, a lot of applications within countries such as South Africa, developing countries, to allow for enhancement of existing materials, which may not have been utilized in its present form, in some unsealed applications. And this has actually, the results coming out from research have actually identified that these have been performing well and offers a sustainable approach to those sorts of applications.
Thank you. Any more questions? Okay, another, Mr. Bridgemohan.
Yeah, I mean.
Okay, was a particular design of experiments used for the mixtures?
Which mixtures actually, because this is a conceptual framework, no data was actually collected to it.
Okay. They didn't specify what mixtures.
Yeah, because when I referred to some experimentation, but not on this particular material in this research.
Okay, the person said they misinterpreted. Okay. Any more questions for Mr. Bridgemohan? Okay, Professor Ray, we are nearing the end of the afternoon session. We are
almost in the end. Thank you, Mr. Bridgemohan, for your very important presentation today. It's very informative of the work that you are presenting. I appreciate your time, and